Hi everyone. In this video we're going to go through section 4.3 in your textbook, which is a pretty short, sweet little section. I want to emphasize something as we get started here though, and that is that I really do not expect you to memorize everything you see in these slides. I'm going to specifically point out the things that you need to really remember or commit to memory, things that you'll need to memorize for the exam. But for the most part, excuse me. For the most part, the section 4.3 is just something that I want to make sure that you see, that you understand. So, try to pay attention and follow along. But not all of this is absolutely, something you need to memorize. So just keep that in mind. We're talking about the coefficient of determination. And so know that when you see capital R squared, what we're referring to is also the same thing as the coefficient of determination. So know that name. Notice, by the way, this is different from lowercase r. And in lowercase r, we were talking about the linear correlation coefficient. So the coefficient of determination is something completely different. Those are not the same. Easy to get those mixed up though, so that's why I pointed it out. Now if we want to get the coefficient of determination, the fastest way is to, number one, create a scatter plot in Excel. Number two, add the linear trend line to the graph. And number three, notice that checkbox that says display R squared on the graph. And we've done this before in previous videos, but let's go ahead and do it again, just to demonstrate one more time. So here's a blank Excel workbook, and first thing we're going to do is punch in some numbers because I need both a predictor variable and a response variable for me to put together a nice scatter plot. So random numbers is 1, 3, 5, 7, 9, 11, and maybe then 0, 2, 4, 5, 6, 8, I don't know, something like this. Gonna make a scatter plot, so select this region, insert scatter plot like this. Okay, so far so good. Green plus sign, check the trend line to put in the trend line, and then more options, display R squared value on chart. That's what we want right there, the R squared value. This is my coefficient of determination, and Excel just gives it to you nice and easy if you create a scatter plot. So remember that. And remember what I put in this green box down here. It says R squared is called the coefficient of determination, and it represents the proportion of total variation in the response variable that is explained by the linear model. This is very, very important. If there's one thing that you take away from this, R squared is the proportion of variation that's explained, right? And let's think about this for a moment. If I'm creating a linear model, I want my linear model to explain all of the variation in my response variable. I want it to explain as much as it can. And so basically, I want R squared to be close to 1. Because 1, if that was the proportion of the variance that was explained, that would say we're explaining all of the variance in the response variable. And so we have a really good linear model if it can explain all of the variance. So we want R squared to be close to 1. 1 is going to be the maximum value. And this is the idea, is we want R squared to be larger. Okay, so again, reusing a model from previous videos. This orange line is going to be the sample mean. So the linear model is here in green. If I let this orange line here be the sample mean, and I'm going to take out some of those blue dots, some of the measurements, just for clarity, and I'm going to zoom in here on this particular section of the graph. So in the next slide that I'm about to flip to, it's that sort of area of inset with the red dashed boundaries. So now that's what we're looking at. So that blue dot from before, that's now what I've marked y. Remember, I use y hat for my model because hat means prediction. And I'm using the over bar for the sample mean right here. So remember, the bar means the sample mean. Okay. So this, again, to refresh your memory, this is the residual. So this is the difference between your measurement and the prediction for that measurement. The deviation is the difference between the measurement and the sample mean. And this is the new part, is what we call the explained deviation. So out of that whole deviation, part of it is explained, and part of it is left behind as the residual. So even after we created the linear model, we still didn't explain part of the deviation. That's what we call the residual. There's different words we could use for these, so make sure you know that when I say deviation, residual, or explained deviation, this is what we're talking about in terms of the math, in terms of the differences. And that, of course, means that the residual plus the explained deviation is equal to the deviation total. I could also call these. So notice I changed the vocabulary words on the page now. Same graphic, but we can also call the residual the unexplained deviation. And we might call the deviation the total deviation. And so in this case, again, it should make sense that the unexplained deviation plus the explained deviation is equal to the total deviation. So again, the explained deviation is saying that, hey, when I upgraded from the constant model to the linear model, this is how much more of the response variable's deviation that I was able to explain. So it's kind of good to have explained deviation that's saying, hey, my linear model is actually explaining some of the phenomenon that we observe. It's bad to have unexplained deviation, good to have explained deviation. Total deviation, it just is what it is. And again, I'm just sort of presenting this in many different ways, so hopefully you're following along and just mentally agreeing with what you see at the top of this slide. And what I pointed out, what I've shown you with graphics, is up here in the top of the slide, here in this black box right here. This is what we've demonstrated so far. This is what I've shown so far. So the total deviation is just the unexplained deviation plus the explained deviation. And in this blue box, I haven't done anything to prove this to you, but I'm telling you that it's true, and I hope you take my word for it, because it's a little bit outside the scope of this course for me to prove this to you. But just coincidentally, all of this blue box is true for the model as a whole. So when we take the linear model with the data set, we'll find that the total variation in the response variable is equal to the unexplained variation plus the explained variation. And so what we're going to use for total variation is SST. That's the acronym, right? Sum of squares total. What we use for unexplained variation, we call this the sum of squared residuals, hence SSR for sum of squared residuals. And then SSE, maybe short for sum of squared errors for all of the explained, sum of squares explained, my bad. Sum of squares explained. So you're summing up all the squares of the explained variation. Okay, now what we're going to do is we're going to take this blue box from the previous slide, and what I want to do is divide both sides of this equation by the total variation, right? And so kind of what we have going on up here is, let me change to a green color. I have SST is equal to SSR plus SSE And what I want to do is just divide through by SST. When I do that, I get 1 is equal to SSR divided by SST plus SSE divided by SST, right? So this is this right here. That's why I said 1 is equal to the unexplained variation divided by the total variation, and plus the explained variation divided by total variation. And so these are ratios. The ratio of the unexplained to the total and the ratio of the explained to the total. And in green here, what I've highlighted in green specifically is the ratio of the explained variation to the total variation, right? This is the ratio of explained variation to total variation. You might see that it's the proportion of the total variation that's explained. And so in this case, this right here, that term is just the same thing as r squared. And that's why I've replaced it with r squared here. And then, of course, rearranging this equation just by subtracting that term from both sides, you get that final equation down there, which says that r squared is equal to 1 minus the ratio of unexplained variation over total variation. And so this gives us basically two completely valid ways that you could calculate r squared, right? So we can calculate r squared by hand by summing up the explained variation and dividing by the total variation, or we could, take 1 minus the ratio of unexplained variation to total variation. And remember over here in these formulas, the y hat is your prediction, the y bar is the sample mean of your response variable measurements. Y just represents one measurement, and then the capital Greek letter sigma means that you're going to sum up that particular term for each measurement in your data set. Now you can do that, but there's also a shortcut to calculating the coefficient of determination, and that is you can just square the linear correlation coefficient. So if I find the linear correlation coefficient, which we've done in previous videos, you can also find the coefficient of determination that way just by squaring it. So keep that one in mind as well. It's an important shortcut. Also, let me show you with Excel that if I create this scatter plot in Excel with my little data set here, and I used the trend line over here, and then under trend line options I click display r squared value on chart. Then if you want the value of your linear correlation coefficient, all you really have to do is type in equals, punch in by hand the value of r squared, so 0.9827 in our case, and then do raised to the power 0.5, and that takes the square root, and so this is the value of lowercase r, the linear correlation coefficient. Just to double check and make sure that works, remember equals CORREL, open parentheses, select your predictor variables, select your response variable array, close parentheses, and then hit enter, and you can notice I get the same linear correlation coefficient. So proof of concept, proof that it works. And that will be the end of this particular video. Where again, the things I want you to memorize, I've mostly put them in green boxes here, which is if you square the linear correlation coefficient, that gives you the coefficient of determination, or if you take the square root of the coefficient of determination, that would also give you the linear correlation coefficient. So these are not the same thing, but they are related. Other things you have to remember is that r squared is the ratio of the explained variation out of the total variation in your response variable. When we say explained variation, we mean that the part of the variation that's explained by our linear model. And for the rest of this stuff, I think it's nice to keep in your head this visual of what it means to be a residual and a deviation, what we mean by explained deviation and unexplained deviations. So I hope this visual lives in your head whenever you think about linear models. And then, like I said, make sure that you know the meaning of this and how to interpret a value of r squared, right? So it's one thing to be able to calculate it. It's another thing completely to be able to interpret what this means. So I guess the last thing I should do before this video is over is I'm going to show you on a TI-84 calculator how you might find these values. Okay, so here's my TI-84, and what I'm going to do is go to Stat, and then Edit to punch in my list of numbers, and my predictor variable is 1, 3, 5, 7, 9, 11. And my response variable values are 0, 2, 4, 5, 6, 8, like that. So I go to Stat again, and then I go over to Calc, and then go down to Linear Regression, and I hit Enter, and then again down to Calculate, and hit Enter, and that is going to tell me the coefficients for my linear model. So y equals ax plus b. Remember what we've been calling a, the slope of the linear regression model, we've been calling that b subscript 1, and what they call b, we've been calling b subscript 0. Keep that in mind. Your calculator calls them something different. But notice it doesn't tell us what the linear correlation coefficient is, and it doesn't tell us what the coefficient of determination is. So respectively, it doesn't tell us what lowercase r is, and it doesn't tell us what capital R squared is. If you want to know that from your TI-84, it's pretty annoying, that they make us do this, but I'll show you how you would find it anyways. Do you see where it says catalog in blue above the 0 button? That's what we want. So we're going to click second 0 to pull up the catalog. And then I think some student told me this at one point, if you click the down button like 53 times. I can't really remember how many times it is exactly, but it's quite a few times. But you've got to scroll down to where it says diagnostic on. And when you get to diagnostic on, that's what we're going to click. So make sure the little arrow is next to diagnostic on. Hit enter. Hit enter one more time and it'll say done. Now let's go to Stat, let's go over to Calc, let's go down to Linear Regression, hit enter, go down to Calculate, hit enter, and now a little bit more magic happens. We actually get to see the value of our coefficient of determination, which is r squared, and the value of our linear correlation coefficient. And you'll see that those are exactly the same as what Excel has told me they are in the background here. All right, so that's how you do it on a TI-84. Yeah, I know it's annoying that you have to go to the catalog to find diagnostic on, but hopefully that helps you. Anyways, see you in the next video.